Connaissance,
recherche,
sciences,
sciences,
mathématiques,
théorie,
physique,
philosophie,
conférences,
archéologie, nature.
Well, thank you very much, Stan, for inviting me here, and also Christophe Callier for the nice discussions we've had. It's a pleasure to be here, and an honor, of course, to be at this venerable institution. My topic today is music and biological evolution. Well, the strange power of music to engage our minds and stir our emotions has fascinated thinkers for thousands of years. Around 400 BC, Plato remarked that rhythm and harmony find their way into the inward places of the soul. Well, even though interest in music in the mind is very old, the study of music in the brain is very young, and it's just in the past decade that a community of researchers has really emerged that's devoted to this topic. And this youth of this field is partly reflecting the youth of the technologies that it relies upon, including brain imaging, which allows us to look inside living human brains as they process music. And one thing we've discovered already is there is no single music center in the brain. In fact, the story is quite the opposite. Let me give you one example from my colleague Stefan Kolsch in Germany. This is an image of a human brain from the left and the right side. This is an ordinary non-musician listener. And in this experiment, listeners heard either simple or more complex harmonic passages of music played on a piano. So there were no words at all. And the regions that are shown in red are regions that were more metabolically active when the person heard the more complex harmonic sequences compared to the simple sequences. And what's interesting is the core auditory regions of the brain are around here. And we don't just see activations in those areas. We see activations in many regions of the brain, including frontal regions known to be involved in abstract thinking, and on both the left and the right side of the brain. So clearly music is not just a right brain phenomenon. And this is just one study showing brain responses to one aspect of music, the harmonic aspect. If I overlaid pictures from multiple studies showing areas that are responsive to musical rhythm, to the emotions we feel when we respond to music, to the memories, to the timbre and so forth, a great deal of the brain would actually be shown in color. In fact, we could update Plato's quote and say rhythm and harmony find their way into almost every nook and cranny of our cortex and even lower centers of our brain. Well, today I want to talk about how neuroscience is giving us a new perspective on a very old question about music and the mind. This is a question that dates back to Charles Darwin, and that is, what is the relationship between music and biological evolution? Now, in his 1871 book, The Descent of Man, Darwin spent several pages discussing music. Now, why would he do this? This is one of the most important books in the intellectual history of our species, and he's arguing that humans are not a product of special creation. They actually evolved from lower life forms like every other species on the planet. Why would he bother talking about music? Well, Darwin had some beliefs about music. He believed it was universal in human culture. He believed it was ancient in our species, and he believed it was powerful in human life. And in all of these respects, he was right in ways that he himself could not even have imagined. Music is universal. In all the cultures that have been discovered since Darwin's time and before Darwin's time, music is always present. It's just like language. It's just always present in human culture, no matter how small the culture is. It's very ancient, and this is a picture of a fragment of a bone flute made from the wing bone of a vulture that was unearthed at a cave in southern Germany a few years ago. This flute was played by a member of our species who was an Ice Age hunter-gatherer. When this flute was last played, woolly mammoths were still alive. We were not the only species of humans on Earth because Neanderthals were still alive. And the oldest cave paintings here in southern France were thousands of years in the future because this flute is over 35,000 years old. So music is very ancient. And music is very powerful. I think intuitively we, especially those who love music, feel music as a powerful force in human life. But this is neuroscience gives us a new perspective on this as well. These are images from colleagues in Montreal who have imaged brain activity in individuals listening to instrumental music that they love. They select their own music and they have strong emotional responses to this music. So again, no words, purely instrumental music. And they look at activities in the brain at peak moments of this musical experience that are associated with chills that sometimes people get when they listen to music, the tingling feeling, the shivers down the spine. And they see activity in a number of regions of the brain involved in emotion and reward, but what's particularly interesting are the activations in these deep and evolutionarily ancient brain centers, the ventral tegmental area and the nucleus accumbens, areas involved in providing pleasurable rewards to the brain in the form of dopamine signals, usually associated with biologically important behaviors such as eating and reproducing, and yet here being activated by purely instrumental music. So it's quite interesting. Well, Darwin felt, based on his beliefs, that music must have had some sort of biological origin. It must exist because it helped our ancestors survive somehow, to have these qualities of being ancient, universal, and powerful. And to explain it, he turned to a theory that he developed called sexual selection, which he spent much of his book actually discussing with respect to other species. Sexual selection is a well-accepted idea in evolutionary biology, and it's thought to help explain elaborate displays and traits of organisms that don't necessarily help them in the day-to-day struggle for existence, but they help them attract a mate. So, for example, the male peacock carries behind him an enormous tail, which is certainly no help when it comes to finding food. He has to drag this big weight behind him or escaping predators. But it helps attract a female. So a male peacock will fan the tail and do an elaborate shimmery display to attract a female. And that's a picture. Birdsong is thought to be another example of sexual selection. Many species of birds sing, and it's the males that sing these elaborate songs in order to attract a female or to defend a territory. Darwin was quite aware of these behaviors and felt that sexual selection could explain them, and he felt that perhaps that could explain our musical abilities as well. And even speculated that our ancestors had a kind of pre-verbal form of communication, a musical proto-language, sort of singing without words that we use to attract mates as part of courtship. And maybe that's why it evolved in our species and has such emotional resonance for our species. Well, as a theory for the origins of music, this has a few problems. First of all, sexually selected traits are typically what's called sexually dimorphic. They're different in the male and the female. So it's the male peacock that has the tail, and it's typically the male bird that sings. But this is not how music works in our species. We have no evidence that males and females have any significant differences in their musical abilities. Also, these traits typically emerge around the time of reproduction and attraction of mates, whereas music appeals to children from a very young age. And we could go on for a while about the problems of this theory. But the larger significance of this theory is that it set the stage for adaptationist theorizing about music, the idea that music was not just a cultural invention, it was something that arose by biological evolution in our species, the capacity for music. And there are now many theories being discussed today about this. I'll just give one other example of a theory that's currently getting a lot of discussion in the literature. The idea that music has something to do with promoting social cohesion. Now, cross-culturally, music is very often a social activity. I know today many people walk around with iPods listening to music by themselves, but cross-culturally and in many cultures, music is often social. And this is an example of an image taken from Captain Cook's voyages to Tahiti in the 1700s, showing a group of Tahitians dancing and drumming. And the argument is here that music is a social activity that bonds people together, that makes them feel connected emotionally to each other. And that perhaps this was its function, that human groups are characterized by all kinds of forces that drive people apart, conflict over resources, whatever. And but in our ancestors, the theory is that to survive, groups had to cooperate. Members of groups had to cooperate with each other to outcompete other groups. And perhaps music was one way of getting everybody emotionally feeling connected to each other, so they were more cooperative with each other outside of musical context. This is just one of the theories being discussed today. Well, there are now a menu of these theories of adaptationist reasons why we have music, but there are also many skeptics. And an early skeptic was the very famous psychologist William James, who wrote in his foundational book, The Principles of Psychology, that the love of music is a mere incidental byproduct of the nervous system. It has no zoological utility. It just arises because we have complex brains that evolved for other reasons. It's something we can do, but it's nothing that has any biological significance. Continuing in that vein, a modern skeptic has been Steven Pinker, who in his popular book, How the Mind Works, wrote that as far as biological cause and effect are concerned, music is useless. It appears to be a pure pleasure technology. something we do because it pleases us, not because it has any larger significance. And this quote, I suspect that music is auditory cheesecake, an exquisite confection crafted to tickle the sensitive spots of at least 6 of our mental faculties. So he argues that we have adaptive mental faculties like language and motor control and emotional vocalization and so on. And music parasitizes those faculties and brings us pleasure because it activates them in interesting combinations. So there's now this kind of polarization in the literature between these positions, that music is an evolutionary adaptation, which is innate at some level and biologically powerful, and that music is a human invention, that it's really biologically superficial, nothing we should pay that much attention to from a biological standpoint. My question today is, which of these views is favored by brain science, this revolution in the last decade of looking at the brain and music? And my argument is that neither of these views is supported by music in the brain, that I think research supports a different perspective, that music is something I call a transformative technology. That is, it's invented, but it's biologically powerful. Now, I should specify by what I mean by biologically powerful. I mean that regular engagement with music can have lasting effects on non-musical brain functions, such as our linguistic abilities and our attention and so forth, outside of the musical domain. And this can occur in ordinary people, not just in professional musicians. And the key idea here is mechanisms of brain plasticity. That is, long-lasting changes in the brain structure and function driven by musical experience. Okay, so I'm going to base my talk in neuroscience, but how can neuroscience really address these issues about music and evolution? After all, we have wonderful brain imaging machines, but these are not time machines. We cannot go back and see what happened in evolutionary time. But we can infer some things. In biology, especially neuroscience, adaptations that involve complex behavioral traits are often associated with some degree of brain specialization. Oh, I've jumped ahead. So let me give you an outline of the talk. So basically, I'll talk about evidence that music is invented, arguing that certain special aspects of music cognition have hidden connections to non-musical brain functions. And then I'll talk about evidence that music is biologically powerful in the way that I've discussed, and then discuss some possible reasons why music is universal without being a product of biological evolution. So back to the topic about what neuroscience can tell us about evolution through brain specialization. Complex traits that have evolved for functional reasons usually are associated with brain specialization, and birdsong is a great example of this. Now, we know that certain species of birds learn their songs. They learn to sing. Other species don't. But species that learn to sing have been studied extensively by brain scientists, and learning to sing complex songs is associated with many specialized centers and connections in the brain, some of which are shown here in this anatomical schematic of a bird brain, especially auditory and motor areas that are interconnected. So, in other words, evolution leaves a signature in the brain of some degree of specialization for an ability. So we can ask, are there specialized centers and processes for music in our brains? So let's start with musical pitch and some special aspects of musical pitch. Now, pitch is a basic feature of auditory signals. It's how high or low a sound is. As I talk, my voice goes up and down. It's natural. It changes in pitch. But in music, pitch takes on more complex and interesting perceptual qualities than just high and low. Let me give you some examples. So I want to play a little simple German folk melody without any words, just a tune. And somewhere in this tune is an odd sounding note. See if you can spot it. So for most people, there's a note in there that sort of sticks out as not quite belonging or sounding odd in some way. But it's not just too high or too low. It's sort of in the wrong category, and we'll talk about that more in a minute. It has sort of an abstract quality of not belonging. Let me give you another example. I'll play a couple of melodies now. These are short melodies. Again, they'll be unfamiliar. But just pay attention to the whole melody and listen especially to the last note and try and decide for yourself if it sounds like a good, stable ending for the melody or if it sounds incomplete, as if the melody must continue in order to be finished. And what I'm going to do briefly is escape and turn up the volume a little bit. Okay. All right, here we go. Here's the first melody. Okay? Complete or incomplete? Now listen to the next melody. And for many people, that doesn't sound complete. You need to go to here. to finish that second melody, to make it sound like it's resolved. Now, let's listen to the last pitch of the first melody and the last pitch of the second melody. They're physically identical pitches, but they're being interpreted in different ways by your brain. In the first case, it sounds like a good ending point, what's called the tonic or most stable pitch in key. And in the second case, it's what's called the leading tone, an unstable pitch in the key. So these qualities of tension, resolution, stability, instability are other abstract qualities that pitch takes on in a musical context that it doesn't have in, like when I speak, for example. It's not just high or low. So these are special aspects of musical pitch. Are they processed by some special brain mechanisms? And how does pitch even take on these qualities? Well, pitch participates in music in a phenomenon known as tonality, which is not unique to Western music, but is well demonstrated by Western music. It's a uniquely musical system for organizing pitches. So unlike my voice, where the pitch just sort of slides up and down, there are discrete pitches. For example, on a piano, there's 12 notes that separate an octave or doubling in pitch. And there's stable scales and intervals that are played when you play music. So for example, if you play in a single key within this Western system, you'd select 7 out of 12 of these pitches to emphasize. And then there are structurally important pitches within that subset and so forth. So there's differential emphasis of certain pitches. So there's structure at multiple levels, discrete elements being combined in principled ways. And this leads pitches to become part of abstract cognitive categories. So for example, you can have an out-of-key pitch, as in that first little German melody I played for you, or a tonic, or a stable pitch, or a leading tone, an unstable pitch. And these are special perceptual qualities that go beyond just being high or low or psychophysical. So these, again, is something very special about pitch in a musical context. Now, tonality, as I mentioned, is well developed in Western music. We have harmonic structure, which really brings this out. But many musics have basic tonality, this use of pitch in abstract ways, where tones play different structural roles. And pitches have these qualities of tension and resolution. You see this in Indian music and Chinese music, so this is not a uniquely Western thing. In fact, it seems quite widespread in the way humans organize their musical systems. So for example, in Thailand, they have different scales than we do, but they still have this structural ways of using pitches. Okay, so what brain mechanisms do we use to process tonality? Well, what's interesting is the early evidence from brain science suggested that tonality was processed in a very special way, having nothing to do with any other aspect of cognition. So you had these brain damage cases that after stroke, they seem to lose sensitivity to this abstract aspect of music. Though they can still hear higher or lower, they can still tell same or different, and so forth, based on low-level pitch processing. And they didn't seem to have language problems or other kinds of mental problems, so it seemed unrelated to other kinds of domains. Some of the phenomena that were described were amusia without aphasia, patients that had strokes that had music problems but seemed normal linguistically, and vice versa. And these were very compelling dissociations. Isabel Peretz has discussed these at some length, suggesting that tonality is processed in a very specific way in the brain. This is just one case study that was written by Alexander Luria, of a composer who continued to compose music even after he had strokes that affected his ability to produce language. So he couldn't speak, but he could still compose music. So these striking dissociations. So this is why it was a bit of a surprise when we began neuroimaging of healthy human brains and looking at what happened when people processed tonality. And what we found was overlap in the brain signals and brain areas that are involved in processing the linguistic grammar, the structure of ordinary spoken language. This was first shown in my research in the late 1990s using evoked potentials or brain waves, which you measure from studying patterns of brain activity from the scalp, but it's been shown in many labs now using different techniques, including magnetoencephalography, which measures the magnetic fields produced by brain activity in the cortex, functional magnetic resonance imaging, and most recently by studies that actually use implanted electrodes in human brains, this is not a very common technique, but it's used with patients that are being operated for surgery, and you can put in grids and so forth. And one interesting finding from many of these studies is the activation of Broca's area, painted on this anatomical slide, on the left inferior frontal convolutions of the brain. A region known to be important for language processing and grammar processing is activated by processing tonality and purely instrumental music, these abstract qualities of tonal music. So this was quite interesting, and it raised, well, first of all, why? Why would tonality activate these language mechanisms? Well, as we've discussed, it involves discrete elements that are combined in principled ways. You don't just throw pitches together randomly. There's many levels of structure. These are hierarchically organized sequences that are a product of this, that are produced by this kind of way of organizing pitch. And you get as a result, abstract structural qualities of sounds. And these are all properties of language, of language as well. Language has discrete elements and principles by which they're combined. So words are combined in principled ways. They're combined into hierarchically organized sequences, and as a result, you have abstract structural categories. For example, the subject of a sentence versus the object, or a noun versus a verb. Now, I'm not arguing that music has nouns and verbs and subjects and objects, but it has these abstract cognitive categories, and so does language. And perhaps music is using some of the same mechanisms as language. So in order to account for both the dissociation between music and language in the neuropsychological studies and this overlap in brain imaging, you have to have a framework that can account for both of those things. So in 2003, I proposed a framework for this, which I call the resource sharing framework. And I think I can give you the intuition in a fairly straightforward way, though the details are quite complex. The intuition is a distinction between domain-specific knowledge that really is very specific to a particular domain, and domain general processing that is shared with other domains. So here's an example. If you know this, if you see this image and you know the game of chess, you have a lot of domain-specific knowledge that is activated right when you see this picture. You know that's a king, you know that's a queen, you know that's a bishop. This is knowledge that is very specific to chess. It doesn't really apply to any other aspect of your life. And yet, when you go to play the game of chess, are you just using chess-specific brain mechanisms that are devoted to chess and are not used for anything else? It seems unlikely. When you play chess, you're probably putting together a kind of a combination of brain mechanisms that have other jobs in your daily life. For example, strategizing, spatial cognition, sequencing, imagining what another person is thinking, what's called theory of mind. And so you have a domain-specific knowledge base, but when you go to use it, you use shared brain mechanisms with other domains. And this is the intuition that I'm proposing for music. Your knowledge of harmony, of chords, of keys is very specific to music. It doesn't relate to anything else, and it can be selectively damaged. But when you go to actually process music, you use mechanisms shared with other domains to activate that knowledge and put it together in real time. So this is the resource sharing framework, which was outlined in a paper in Nature Neuroscience in 2003, and also described in detail in Chapter 5 of my book on music, language, and the brain, if you'd like to really read the details, because it really relates very specific theories of cognitive processing of language and music to each other. But just as a kind of cultural comment, I wonder if this is why this phenomenon of tonality is so sticky historically. Why do we still listen to tonal music when the composers of the Second Viennese School, including Schoenberg and Webern and so forth, predicted that tonal music would one day vanish like every other fad and cultural artistic phenomenon? Why Webern said the mailmen will be singing atonal tunes to themselves as they deliver the mail in a short period of time now that we've invented this new system of composing music. Why hasn't that become true? Why do we still listen to tonal music of the kind that was composed hundreds of years ago? Of course, we listen to atonal music too, and much of it is beautiful and compelling, but statistically, many people still choose to listen to tonal music. And could it be that because processing tonal music shares some brain mechanisms with language processing and with the processing of linguistic grammar, which we are very adept at? I think that's one intriguing possibility, even though tonality is completely nonverbal. Now remember, this is a cognitive hypothesis, not an aesthetic judgment. I'm not arguing that there's anything wrong with atonal music. Things can be hard and be very valuable. For example, think of great literature. James Joyce is much harder to read than Michael Crichton, but that doesn't mean that's not an aesthetic judgment, that we would say, oh, Jurassic Park is a better book than Ulysses. It's just a cognitive hypothesis. Some things are harder to process than others. Tonal music may be easy to process for us for a certain reason. Okay, so I've argued that a special aspect of music, this tonality, is actually shared with language in terms of its brain processing. We've taken this to the clinical level now. This resource sharing framework is being used to study language disorders in new ways. So if it's true that language and music share some aspects of grammatical processing, this gives us a new way of looking at certain language disorders of grammatical processing. For example, agrammatic Broca's aphasia, which we published on, and people are beginning to look at specific language impairment. The question is here, you have a patient that has problems processing language, the grammar of language. Do they actually also have some deficits in processing the abstract structure of music? And it looks like they do in the studies that have been published so far. And the goal of this research is really to understand the nature of their underlying processing problems. If they don't just have a language deficit, they must be having a deficit with a more abstract level of processing. Maybe we can use music to understand what that deficit is in order better to treat it. Okay, so we've talked about pitch. Now let's talk about rhythm and aspects of musical rhythm that seem quite special to music and unrelated to other things in cognition. And the aspect of rhythm is very diverse, of course. I mean, rhythmic traditions vary enormously. And you can see that even just the instruments that people play. These Native American frame drums are quite different from the South African West African drums, and there's also rich rhythmic traditions in singing and so forth, like in this Ladysmith Black Mambazo, the South African group. But one thing that's quite common is the use of some kind of a beat, some kind of periodicity that organizes the rhythm. Now, this is not present in every form of music, but it's a very widespread feature of music. All over the world, every culture has some form of music with a regular beat that people often dance or move to. In fact, it's interesting that Nietzsche remarked that we listen to music with our muscles, and I think that's a nice way of capturing this idea that we have this motor, almost involuntary motor response to rhythmic music, this desire to move. Now, moving to a beat seems, at some level, extremely simple. Nodding your head or tapping your foot or bobbing, how complicated could that be? And yet, when we begin to unpack it, as with so many things in cognitive science, you begin to see the complexities. So when people move to a beat, they are anticipating. They're not reacting. It's not like they hear a beat and then move. They're actually, if you ask people to tap to a beat, they're landing right on the beat or even a little before. They clearly have a mental model of the auditory stimulus in their head, which is what they are using to synchronize with. It's very flexible. If the music slows down or you hear a song with a slower beat, you can easily adjust to that, or a song with a faster beat. You can adjust your movements, and it's cross-modal. When people move to music, they typically aren't aiming to just reproduce the music. They're often moving silently in response to a sound stimulus. And this is an unusual combination of things that don't mark any other kind of behavior we see in human rhythmic behavior or in other animals. And it calls on the question of whether there could be, again, special brain mechanisms that evolved to subserve this ability, perhaps in service of these kind of group rituals of moving and dancing together for social bonding. This has been proposed. And actually, it's quite interesting that this ability seems very simple, right? And yet it turns out it's very difficult for many other animals to acquire. In fact, most other animals don't show any of this sort of spontaneous rhythmic response to music. And in fact, if you try to train other animals to move to a beat, it turns out to be quite difficult for many of them. So a paper by a colleague in Mexico using rhesus macaques, which are extremely clever animals, in a laboratory study of timing to see if they could learn to tap to a metronome, something that is very easy for humans, even who've had no musical training, and even for children. He had a couple of monkeys, and he tried to teach them to tap to a metronome just in order to study the neural circuits involved. I think he trained them for 6 hours a day, 5 days a week for a year, and they could not learn this task. The best they could do is respond within a few hundred milliseconds after the metronome click. They could not just learn to tap to a metronome the way that's so easy for us. So this is not something that just comes along with the brain, the complex brain. It seems to be something that is special in some way. And it actually has some clinical significance, moving to a beat. Let me illustrate that for you via a short film. Now, it's just been observed that patients that have Parkinson's disease and other motor disorders that give them difficulty initiating and coordinating movement, sometimes they find music with a beat helps them actually to move. It helps them get moving and keep moving. And this movie illustrates this. This is from Connie Tomino at the Beth Abraham Hospital in New York City. And what you'll see as a Parkinson's patient, the movie starts very quietly. She's sort of frozen. And then a therapist is putting on some music, and then watch what happens, and pay particular attention to her movements in relationship to the rhythm of the music. So this is quite interesting. So she has Parkinson's disease, which involves degenerations in some parts of the brain, deep motor structures, the basal ganglia, that are normally involved in sequencing of movement and so forth, and timing. And she's able to use music as kind of a rhythmic prosthesis to give her the kind of cues that help her move again. So the auditory motor connections here are very powerful. And she's in training. As you can see, she was stepping to the beat of the music. So we're very interested in the mechanisms by which we extract a beat and move to a beat in music at the institute where I work, and we're studying this neurobiologically with brain imaging and so forth. But I won't be getting into that today. I want to focus on the evolutionary issues. In the question of, okay, this is a special aspect of music. It's quite powerful. But is it related to any other aspect of our cognition, any other brain system that is not devoted to music? And I think it is. I think it's related to something that we have, every member of our species has, called vocal learning, which is just simply the ability to imitate complex sounds. Now, this seems very unspecial to us because we all do it. Children learn to speak a language because they can imitate the sounds of their parents. But this is actually a very unusual ability in nature, especially among primates. So it turns out we're the only primate that can do this. Chimps, monkeys, and all the other primates, as far as is known, they have a repertoire of innate calls. They can control when they give the calls, but they don't learn them, and they don't learn to imitate other complex sounds. So this requires some kind of special brain circuitry, and it's been studied a lot in birds because some songbirds are vocal learners. But anyway, this vocal learning, one of the things that it seems to, this is a human brain, a schematic of a human brain. One of the important kind of foundations for it neurobiologically is the connection of auditory areas to motor areas. So motor areas in red and auditory areas in blue. So you see kind of special connections occurring between these areas, which makes sense because when you vocally learn, you have an auditory model which you must reproduce. So you have a complex auditory object that needs to be connected to your motor system, and there has to be constant feedback between them so you can correct what you produce to match the model. Now, we are not the only vocal learning species. We are the only species with speech and language, but we're not the only species that can imitate sound. There are many others that can, including parrots. And this is a schematic of a parrot brain to scale, but now I'll blow it up. And it turns out comparative neuroanatomy work on parrots done by Eric Jarvis at Duke University suggests that some of the same kind of principles are at play. They're vocal learners, they can imitate sound, they have auditory areas, and they have motor areas that have become specialized for this ability to imitate sound, and there are special connections between the two of them. So in this one respect, the anatomy of our brain is actually more like that of a parrot than it is like a chimp, which is so much more closely related to us, because chimps are not vocal learners, they do not have these specialized connections in their brains. So I hypothesized in a paper in 2006 that this connections between auditory and motor systems that were driven by vocal learning were actually the foundations for moving to a beat. That's why we can move to the beat of music, what's called the vocal learning and rhythmic synchronization hypothesis. Now, this hypothesis makes some testable predictions. It predicts that you can never train an animal that isn't a vocal learner to move to the beat of music. So no matter how clever your dog is, or your cat, or your chimpanzee, if it's not a vocal learner, it doesn't matter how much time and resources you expend on training this animal, you'll never get it to move to the beat of music. On the other hand, you might be able to get a vocal learning animal to move to the beat of music. Now, this is a relatively young hypothesis, remains to be tested thoroughly. The monkey example, I think, is an interesting example in that regard. That's sort of a negative example of an animal that has great difficulty. But what about a positive example? Well, we were fortunate to get a chance to actually study a positive example of a vocal learning animal that seemed to actually be able to move to the beat of music. And this came about in a curious way. This is a sulfur-crested cockatoo that was a pet. He was dropped off at a bird shelter in Indiana, in the USA. These are very long-lived animals. They're very demanding socially. It's said that these birds have a personality of a 4 or 5-year-old, but they live for 90 years. So people, after a while, they can't cope with this, and they drop them off at bird shelters. And so this bird was dropped off at a bird shelter, but unusually, the bird was dropped off with a CD of a rock and roll CD. And the owner said the bird likes to dance to this music. The owner of the bird shelter thought this was rather strange, but put on the CD, and the bird actually started to dance. And she took a video which went on to YouTube and became very widespread. A colleague sent this to me and said, this potentially looks like another species can move to music, which has never been demonstrated. So I emailed the owner and said, would you actually collaborate on a proper scientific study? Because with a video on the internet, who knows what's happening? Maybe the bird is just imitating a human that is dancing off camera and so forth. Well, she agreed, fortunately, and we collaborated on a proper scientific study where we took the music that he danced to and we slowed it down and we sped it up to 11 different speeds without changing the pitch. We made sure nobody was dancing off camera, and we videotaped the animal to see what he would do. And lo and behold, he actually adjusted his the movements to stay matched with the beat of the music. The first case of another species spontaneously synchronizing to the beat of music. So I'll show you a couple of videos from our studies now. Now, these are not the YouTube videos. These are from our scientific studies. So there's nobody dancing off camera here. The bird is dancing by himself. And this is published in Current Biology, which has all the methodological details, if you're interested. But I'll show you a couple of examples of these episodes where he was synchronized. So this is slowed down a little bit from the original tempo of the song. Okay? And now let me show you the fastest. This is now the fastest, 20% faster than the original song. And this is an interesting clip. It's a little too fast for him. Watch what happens at the end. So it's interesting. He sort of figures out a way to cope with this really fast music by moving side to side on every other beat. So he's actually doing what's called meter. So he's following the beat at multiple hierarchical levels, which is amazing. It's what humans do. So he's able to do this, and this is not a trained circus animal. This is just a pet who's listened to music, and he's observed humans dancing to music, but so have dogs and cats, and yet he's able to do this, and dogs and cats don't. Of course, with one animal, there's always the question if it's just some freak of nature. Fortunately, in the same issue that we published our paper, Adina Schachner from Harvard published a paper where she took a different approach. She decided to look across, spent the whole summer looking through YouTube videos for dancing animals, and looked at over 1,000. She said it was fun for the first 20 minutes, and then it became work. But she found 14 more species that seemed like they were entrained to the beat of music. Now, these are not controlled experimental studies, but she figured if there were dogs and cats that could dance to the beat, you should see them on YouTube just as well as parrots or other vocal learners. And the bottom line of this study was she found, I think, 14 more species that seemed like they were able to entrain to music. And 13 of the 14 were other species of parrots. There was also an Asian elephant, which turns out to be a vocal learner. So it does seem like, so far, only vocal learners have this ability. So this hypothesis is continuing to be tested, but it's sort of interesting. Now, the significance of all this is that this animal is clearly not, moving to the beat of music is not something this animal evolved to do. It's not got a brain that's been shaped by natural selection for music. And yet it can do this very basic aspect of human music. And I think it's because it has a brain that's wired for vocal learning, and perhaps that's why we can also move to the beat of music. All right. So I've argued that neuroscience suggests that music is a human invention because it has these special qualities of music, like pitch and tonality and moving to a beat, actually seem to have connections to other non-musical brain systems. So where does that leave us in terms of our debate? Evolutionary adaptation or human invention? Well, again, I think neither of these is correct. I think what's increasingly true from my perspective is that the evidence is it's an invention because it's built on other brain systems, but it's biologically powerful. Now, this is where I want to spend some time telling you about examples of biological power of music and exactly what I mean. But I want to point out some parallels here to the theory of neuronal recycling from Professor Dehaene, the idea that a cultural product basically can be built upon other brain systems that evolve for other reasons. The brain systems that evolve for one thing can get recycled to support another brain system. So, for example, in his own work on reading, he's argued that specific brain areas that are evolved to do certain types of spatial cognition can get reused and recycled for this cultural invention of reading. And I'm suggesting something similar, although I'm emphasizing in particular this aspect of music's ability to have impacts on other brain systems outside of music. Okay, so let me give you a couple of examples of the biological effects of music. And these examples have to do with patients that have had strokes. So the first set is a study of cognitive recovery after stroke, and the second study has to do with verbal recovery after stroke. And these are effects that concern non-musicians, and these are persistent effects of music on the brain, not just while the music is on, but lasting effects. And this is an area that's growing now in research. So there's a whole volume of the Annals of the New York Academy of Sciences that is devoted to this recently, and there's a new journal, Music and Medicine, that tries to connect music with medical therapeutic benefits. So in the first study I'll discuss, this was a large study that was conducted in Helsinki. They had 60 stroke patients that were randomly divided into 3 groups. These were patients that had large cerebrovascular accidents on either the left or right side of their brain. So they all had standard stroke therapy. But in addition, one group was assigned to a music listening condition, another group was assigned to a story listening condition, and another group had no additional treatment. So one group had an hour a day of music listening, self-selected music that they enjoyed. Another group listened to stories, books on tape that they enjoyed, and the third group had no additional treatment. And they assessed them post-stroke on 8 cognitive and 8 mood measures. And the therapy lasted for, I think, about 2 months, and they tested them later than that. So these are the behavioral measures that they studied: verbal memory, short-term memory, language, visuospatial cognition, and so on. And then these are the mood measures: tension, depression, irritability, and so on. And these were standardized psychological tests that were given by assessors who were blind to the condition that the subject had been in. So let me give you some examples of the kind of results that were observed. Now I'm going to show you some results for the cognitive tests. And the music group is shown in the circles, the language in the squares, and the control group in the diamonds. Now for most of the cognitive tests, the data looks something like this. So this is performance. Everything's been normalized to baseline performance. So this is change from baseline. Baseline is soon after the stroke. Now remember, the therapy took place in the first couple of months, so right around here. But they're being tested at 3 months and at 6 months. So you're looking for any lasting effects of this therapy. And in most tasks, like visuospatial cognition, what happened was, after the stroke, there was improvement, some natural brain recovery in this task. It didn't matter which group you belonged to. Your brain recovered, and you did just about equally well, whether you'd listened to music or stories or done nothing extra. But there were 2 cases where music group differed from the other group. In both those cases, the music group did better. So in tests of verbal memory, the music group is doing better than either group. This is ability to remember words that you've just heard in a list or words from a story. And in focused attention tasks, they're actually doing better than either of the other groups. Okay. What about the mood measures? Well, again, for most of the mood measures, it didn't matter what group you belonged to. Here's fatigue, 3 months and 6 months, your subjective rating of your own fatigue levels, 3 months and 6 months after the stroke. Doesn't matter if you've heard music or language or nothing else. But again, in 2 cases, it did make a difference, and in both of those cases, the music group did better. So for depression and confusion, the music group is less depression, so better is lower now, because this is less depression on this scale, and less confusion than the other groups. That's sort of interesting. Now, this is just listening to music for an hour a day, and I find this kind of remarkable. People have had a stroke. You think, how can we help this person? You think maybe we could inject some growth factors into their brain or stimulate them somehow. And yet, just listening to music is having these effects. What's going on? What's the mechanism? Well, the authors didn't really have a very comprehensive idea about mechanism. This was more of an observational study. But I have a hypothesis that this might have something to do with stress hormones, which are normally adaptive, but they can actually be bad for your brain if the stress is chronic as opposed to transient. And just to remind you, stress hormones, the one I'll focus on is cortisol, are produced by the adrenal glands, which sit on top of the kidneys, in response from signals from the hypothalamus and the pituitary. So there's this whole hypothalamic pituitary axis. Now, these stress hormones normally play adaptive functions in our lives, but persistently high stress is a different story. And there's a wonderful book about stress and the brain called Why Zebras Don't Get Ulcers by Robert Sapolsky. And why don't zebras get ulcers? Zebras don't get ulcers because in nature, when an animal has a sudden stress, the zebra is sitting there, a lion jumps out and chases it. The zebra is incredibly stressed for the next 10 minutes while it escapes the lion, but then it escapes and it goes back to being a zebra, eating its grass and doing what zebras do. So you have transient stress, and these stress hormones are very adaptive. They get energy, they mobilize energy in your body, they get your heart racing, they sharpen certain aspects of cognition. They're very good in the short term. But zebras don't get ulcers because zebras don't have chronic stress. They don't sit around worrying if they're going to get tenure at the Collège de France, right? They don't have to live with the kind of this stress that we create for ourselves as part of social animals and living in long-term social cultures. And in those situations, these stress hormones, which are chronically activated, can actually damage the brain. And a stroke, we know, is very stressful. After a stroke, your life changes tremendously, and it's been shown that these stress hormones are at very high levels persistently after a stroke. Well, what's the significance of that? Molecular and cellular studies of these stress hormones show that when they're at chronically high levels, they can actually damage the neurons in certain brain structures. They actually physically alter the shape and function of neurons in certain brain structures, including brain structures known to be important for verbal memory and focused attention, such as the hippocampus and frontal cortex. So the hippocampus is a deep brain structure involved in memory, and you all know the frontal cortex is in the front of the brain. So I think, and also there are empirical studies showing that in adults, listening to soothing music actually reduces cortisol levels after a stressful event. So I think if you put these pieces together, you can actually make a hypothesis that after a stroke, the brain goes through a period of neural reorganization. This is actually well known already. And stress hormones could have a negative impact on the brain during this period of neural reorganization, in fact, damaging cells that are in these areas involved in memory and frontal and attention. So music, by lowering these stress hormone levels, can actually facilitate the brain's recovery from a stroke. I think that's one hypothesis. It could be tested, but it tries to explain mechanistically why just listening to music can be beneficial for cognitive function after stroke. Okay, and this, interestingly, music has no negative side effects of the kinds you might get with giving a drug, for example. So the second example, again, is stroke in adults, but this is about verbal fluency. So after some types of strokes, including left hemisphere strokes in certain regions, patients have great difficulty communicating or using language, what's called aphasia. And this is a devastating disorder. You know how important language is for us in our species, in our daily life. Imagine if you woke up tomorrow and you had lost your ability to communicate with language, though you're still an intelligent person. This would be very devastating for you. So what can you do to help these people? There are no drugs you can give at the moment that seem to help. There's no brain surgery or implanted electrodes or anything like that seem to help. What can you do to help? Well, these are a couple of patients that have been studied, by the way. In this study I'll be telling you about, these are the MRIs. You can see these big left hemisphere lesions in their brains. And they have non-fluent aphasia. They just can't seem to get a few words out. Well, one observation that kind of is interesting goes back over 100 years, that some of these patients can still sing. And this is quite striking. They can't get 2 or 3 words out in a coherent fashion in speech, but you ask them to sing an old familiar song, and they seem remarkably fluent. You might not even know they had a brain problem. This led to the development of a therapy. The idea being, well, maybe singing relies on some of the more preserved right hemisphere circuits of the brain. Can we somehow tap into that and help recover some of their language abilities? So in Boston in the 1970s, Martin Albert and colleagues developed something called melodic intonation therapy. The idea being to kind of have patients semi-sing little phrases. And in fact, it's a very simple form of singing because it only uses 2 pitches, a low pitch and a high pitch. And the patient works very closely with the therapist. So this is not just passive listening to music, this is active engagement. And they practice saying these short, very stock phrases like I love you or I love my children. But they don't just repeat them, they intone them. They go up and down between 2 pitches. So the patient would say, I love you, or I love my children. And they'd kind of slow down, they'd intone, they'd tap with one of their hands, and sort of sing these phrases. And the idea is to move to longer and longer phrases until they can produce fairly long phrases in this kind of singing format, and then gradually to generalize to non-sung phrases. And this has been around since the 70s, this therapy. It's one of the few therapies that's available for these patients. But its efficacy and its underlying brain mechanisms haven't really been studied. So a colleague of mine at Harvard Medical School, Gottfried Schlag, is now studying this in a randomized controlled trial format to see if it really helps and how it helps. So he's asking, does it help and how? So these studies are now underway, and the initial results are quite promising. What he's doing, he's comparing this melodic intonation therapy to a control situation where patients have all the same interactions with the therapist. They do the same sentences, but they don't sing them. They don't melodically intone them. They just repeat them with speech. It's called speech repetition therapy. And he looks at their behavioral improvement, and he looks at their brains to see what's happening. So this is an intensive therapy. He's looked at patients that have had 40 sessions of this therapy for an hour and a half each. And he's taking behavioral and neural measurements pre and post therapy, which I think is a really great way to study this. So here are some data from just a couple of patients he's published so far, but they're more underway, being published now, and the results seem to be generalizing. So this is behavioral measures of linguistic recovery. Now these are patients that have been a year or a year and a half post-stroke. So they've had all the standard speech therapy you get with after stroke for aphasia. And this is their baseline performance in terms of linguistic performance. This is correct information units per minute, number of sort of correct phrases that they can produce in a minute, so only about 4. The number of syllables per phrase, so about 2, and their ability to name pictures. So this is baseline for these 2 patients. This one went through melodic intonation therapy, and this one went through this control therapy. And this is after 40 sessions of therapy, and you can see there's genuine improvements here. So an improvement of over 200% in the number of information units, of over 200% in syllables per phrase, and so forth. The control patient also is showing some good recovery. Not as good as the MIT patient, though, and this difference does seem to be holding up in subsequent work. But I think this is quite important because most patients after stroke, at least in the US, they're given a few weeks of therapy, maybe six weeks or a month, and that's it. And the general rule of thumb is after 6 months, you won't see any more recovery. But look at this. This is a year and a half after stroke, and you can still change the brain. And I think that's really great news. But what's going on in the brain? Well, Gottfried Schlag hypothesized that maybe what's happening is these right hemisphere singing regions are being recruited to take over for some of the damaged left hemisphere speech regions. So he imaged them speaking after the therapy, before and after the therapy, to see what the differences were in their brain activation. This is the patient that's been through melodic intonation therapy and through this speech repetition therapy. And these are the regions that are more active after the therapy than before. And what I hope you can see is that this patient is activating a large areas of the right hemisphere when they speak, not when they sing, but when they speak, whereas this patient is not. So it's as if these regions, which probably involved in singing originally, have been retrained and recruited to take over for some damaged language speech functions. And so this is a kind of contralateral compensation for the damaged left hemisphere regions. And even more interestingly, in my opinion, is some results he's recently published on connectivity and how this therapy is actually changing the structural connections in the brain. Now, there are many big fiber tracts in the brain. This is a schematic of some of these tracts. This is the front and the back of the brain, the top and the bottom. This is one of the giant ones called the arcuate fasciculus, shown in this schematically here, which connects posterior and frontal regions of the brain, and it's very important for auditory motor integration. Now, these patients had huge left hemisphere lesions, so this fasciculus was largely damaged in the left hemisphere. But it was intact in the right hemisphere, and so Gottfried imaged this using diffusion tensor imaging before and after the therapy. Now, these images are a little hard to see, but it's sort of like looking into a glass brain. This is the front, that's the back, top, bottom. And he's traced here the arcuate fasciculus before and after therapy in one patient. So after these 40 sessions of therapy. And what I hope you can see is it looks like it's actually changed in structure. It's more organized, it's thicker. We're actually not sure what is happening at the level of single cells, whether they're more axons or more myelination, but something is changing in this big brain structure that seems perhaps to be involved in the recovery based on this therapy. So this therapy is actually changing the structure of the brain. Now, I've given you just two examples, both from adults in stroke, but there are many other examples of biological power of music that are emerging, and these are studies measuring how regular engagement with music influences other cognitive abilities outside of music. So there are studies of reading ability, how educating children in music actually facilitates their acquisition of reading, studies on how it helps focused attention, on second language learning, non-musical motor skills, and so on. And these are studies that are increasingly using both behavioral and neural measures, which I think is essential for trying to understand how music and why music is having these effects. This is a rapidly growing area. I think we'll be seeing a lot more in coming years. But let me, and so I've argued music is an invention, but it's biologically powerful. So now I have to address the last question, which is, if you take this invention view, how can you explain why music is so ancient and universal and powerful? I mean, when we think of inventions, we normally think of fairly culture-bound things. Chess, we talked about the analogy of chess. Chess is not universal and ancient. We're not finding ancient chess sets in these caves in southern Germany. Chess is very culture-specific, and many other inventions are too. But not all inventions are culture-specific. Some have become universal in human culture and are just part of our life, everywhere. And one of those is the ability to control fire. Now, this goes back hundreds of thousands of years in our species' history. And it's present in every human culture. Every human culture knows how to control fire, and we're the only species that does it. And nobody argues that this is a biological evolutionary specialization of our species. It's an invention that is universal because it's universally valued. It gives us things that we all value, no matter what culture we belong to. For example, to be able to cook, to ward off predators, to see in the dark, to keep warm, and so forth. So inventions can become universal if they appeal to universal things in our life. And I think music could be explained the same way. Perhaps music is universal because it does some things that are universally valued. For example, it stimulates our emotions very deeply. And why it does that we'll talk about in the next slide, but almost unreasonably, it has this incredible power over our emotions. It's very useful for organizing rituals. All over the world, every culture has rituals. And, Speaking of rituals, that's a ritual. Answering your phone, which I will not do right now. So think about the happy birthday song, singing happy. Yesterday was my son's birthday. He was very happy to turn 9 in Paris. We were able to go out for the best chocolate mousse in Paris. He was in heaven. And we sang him happy birthday, as you do when you have a family member or a friend that's has a birthday. Why do you sing happy birthday? It's not about the beauty of the music. Usually, if you listen carefully, it sounds horrible. It's about collectively recognizing somebody's birthday. It's a ritual, and music is terrific for that. It's set apart from your daily speech activities. It gets everybody together and does something that everybody can recognize as a special thing. So music has that property. And music aids verbal memory. This is all over the world. Music helps people recall verbal information. All the ancient epics, the Iliad, the Odyssey, the Vedas, the Gita, they were all sung. They weren't just spoken. So music helps us encode verbal material. And so music has these properties all over the world. And I think that could be one reason why it's universal, because these are all things that are valued in every culture. And music has become so important to us. It's sort of a way of expressing our identity now. And this, I think, is nicely captured by the fact that they put a couple of records on the Voyager spacecraft when they knew the spacecraft was going to run out of fuel and leave our solar system. In fact, I think it has left our solar system recently and float into interstellar space. Its batteries are going to run down. So what can you do with it? Well, you can put a message on there to convey what we are as a species to other creatures that might come across this object. And one of the things they put on there was lots and lots of our music. And so I think it's an invention that has become very deeply emblematic of us. So finally, there's this lingering question, which is, why is music so powerful emotionally? How can you explain that without appealing to evolutionary specialization? There's an interesting paper that was published in Behavioral Brain Science that I think gives us one possibility, called the multiple mechanisms theory. The idea that listening to music gives rise to emotion in multiple ways. So in this paper, they argue that there's at least 6 different mechanisms by which music can evoke emotion in our brains. Brainstem reflexes, conditioning that's associating music with events in our lives, emotional contagion, the way music can sound like sounds of a happy voice or a sad voice, and that can spread emotionally, the imagery that music can bring us, the memories that it evokes, and properties of expectancy and surprise. So none of these systems are unique to music, but music may be unique in its ability to co-activate multiple brain systems that are involved in emotion. And Stefan Kolsch has published a nice review paper recently in Trends in Cognitive Sciences, or Neurosciences, I think Trends in Cognitive Sciences, arguing that, based on brain imaging data, that music activates many of the emotion systems of our brain. We don't just have a single emotional system, we have many emotion systems involving many brain areas, the accumbens, the amygdala, the hippocampus, the cingulate cortex, the temporal regions, and so forth. And none of these evolved perhaps to deal with music, but music may be unique in its ability to co-activate all these systems at the same time, and perhaps that's why it's so powerful. So to conclude, the main conclusions of this talk is that I believe music uses brain systems that evolve for other purposes. Yet it can shape those systems within the lifetime of an individual, and that's the crucial fact about it from my perspective. It's a biologically powerful invention, or what I call a transformative technology of the mind. And I have a chapter that outlines this in more detail if you're interested, available on my website. So I began with Darwin, so let me end with Darwin. What is the relevance of a Darwinian perspective on the biological study of music today? Well, if you are committed to studying adaptationist hypotheses, then Darwin's theories may not be that relevant today, because sexual selection as a theory for music is not that prevalent as a theory anymore. But if you look beyond this specific hypothesis that Darwin had to his general method of doing biology, I think Darwin's perspective is very relevant for the study of music in the brain, because Darwin was essentially a comparative thinker. He thought about animals by comparing them to each other, tried to infer evolution. Darwin didn't have a time machine either, but he inferred things about evolution by comparing species to each other. And I think we can infer a lot about music and how it works by comparing music to other domains, not just studying it as an isolated brain system, but always comparing it to things like language or spatial cognition or numerical cognition or what have you. And also, this comparative approach, well, if we use that aspect of Darwin's research, his way of doing research rather than his specific hypothesis about music, I think we'll end up learning a lot about how music works and about how our minds work. Thank you very much.